Hello, this is Dr. Jim Brenner. I'm recording this for the electrical conductivity lab for the basics of making. Okay, to start out with, I would like you to go to assignments, electrical conductivity / salinity sensor, Arduino, total dissolved solids. We buy our electrical conductivity sensor from DF Robot, and technically, this is measuring electrical conductivity, and that would be twice the total dissolved solids concentration, because for the sodium chloride that's used for this, it dissolves into 2 ions. It says to go to the gravity tds.zip, and it's got everything it does, but I would like you to focus on tdsserial.eno in here. You can download the tds calibration.eno if you want to calibrate this as well, but we will focus on the tdsserial.eno. .eno is short for Arduino, so that's an Arduino code program. The wiring diagram looks like this. Will be your Arduino. The red wire goes to 5 volts, the black wire goes to ground, and the yellow wire goes to A1 on the analog in. This is the electrical conductivity shield, which already comes pre-soldered, and there's your electrical conductivity sensor. And I'm going to stop sharing and switch over so that you can actually see what's going on here. There is the electrical conductivity sensor sitting in the appropriate solution. There's the Arduino and the shield. We're going to start out with the 100 microsiemens per centimeter solution. It says 47 ppm TDS. You would think it would be 50. The reason it's not is because there are actually other things in there. It's not absolutely purely sodium chloride, although ideally it would be. If it's 100 microsiemens per centimeter, it should be 50 parts per million of the salt, but this says it's 47 in this calibration standard. If you load the .eno file in by going to open and then finding the appropriate downloaded file, and then finding, looks like I'm using TDS, I guess I'm using the TDS serial for this one, which is buried in a directory right now. When you try to open it, the first time, it will place it into the appropriate folder. And you can see that this was written by Jason Ling of DF Robot. Actually, you can't see that. Let me switch this over so that you can see the computer. And when you download it, it'll be in the downloads. And when you open the TDS serial file, it will generate its own little directory. It'll ask you to put that in. Now, when you go to run this, there is one possible issue. I want you to notice where it says serial.begin 115.200. That's the so-called baud rate at which the communications happen. And by default, if you go to the serial monitor, after you try to compile this and run it, if you go to the serial monitor, if it's in the standard of 9600 baud, you're going to see very strange characters there, And it's because the serial connection, basically it's a telephone connection, is not set to communicate at the right frequency, the right baud rate. And so you've got to change it to 115/200 so that they're consistent. And then you'll see that it's reading TDS value 51 parts per million for this one. Ideally, it should be 50, but according to the bottle, it says 47 parts per million if you're dealing with 100 microsiemens per centimeter. And that is quite literally half the lab. Now what we're going to do is, after rinsing this, we're going to switch it into a different container. You can see that it's reading 0 parts per million right now when it's not sitting in the water. And now I'm going to switch it into a 1,000 micro Mo. So I need to stop sharing for a second and show you. I've switched the container, although it doesn't seem that easy to see. I've switched to 1,000 Siemens per centimeter at 25C, and that is giving us a reading of 450 parts per million. Ideally, it would be giving us a reading of 500. Why is it not? Well, things are not absolutely perfectly linear in terms of response between conductivity and TDS, the total dissolved solids. Ideally, it would be. You will record those two concentrations at 100 microsiemens per centimeter or 47 parts per million dissolved solids, and 1,000 Siemens per centimeter, which should be at 500 parts per million of total dissolved solids. And you can see that it's not exactly that. Should be a nice linear relationship between your signal and the concentration. It's very slightly nonlinear. You will have to define 3 points. You've got 2 concentrations plus the 0, and ideally it would be a linear relationship. It won't be perfect. And on that note, we are done.